Hi everyone, what's up? Welcome back to my tutorial channel. Daniel's here and today I'm gonna walk you through topic 6, the normal distribution. This topic is divided into 5 parts and today I'm gonna talk about the first part, the normal curve. So in this part, I'm gonna first show you how to build up a density curve to describe a population. Then I'm going to introduce the normal density curve, how to compute the z-scores, and I'm going to introduce some problems relating to finding the area under the probability density curve. So first, let's get started off with the density curve to describe population. So the density curve is basically created based on the histogram. Remember in the lesson of descriptive statistics, I showed you how to construct the histogram for a dataset. So here, suppose that we have a large sample size and we are constructing a histogram. Then if the sample size is sufficiently large, we would have a large number of narrow rectangles. So this is an example of histogram with the number of rectangles is large. Here I have 65 rectangles. So this is a histogram for a continuous dataset. To create the density curve, what I'm gonna do is just like for each rectangles, at the top I'm gonna mark the point at the middle of the top of the rectangle. So for each rectangle, I'm gonna have one point, and what I have to do next is just connect them all together. Then I have a curve. So you can see that we have drawn a curve run along with the shape of the histogram. So imagine if we erase the histogram, the rectangles, after we finish the curve. We would have only the line, only the curve. And this curve is called the probability density curve. So here, after I erase the histogram, I have a density curve. And this curve, the shape of this curve is corresponding to the shape of the histogram. So usually we assume that the area under the whole area under the density curve is 1. So let's say this curve goes from 0 to more than 7. You see that if we want to find the proportion of the population between two values, we basically shade the area between the two values under the curve. So here, if you look at this curve, the shaded area is the area between number 3 and 4, and this shaded area represents the proportion of the population with values between 3 and 4. And this shaded area, the area under the density curve between two distinct points, A and B, have two interpretations. The third way to interpret it is just this area represents the proportion of the values from the population that have values between 3 and 4. The second interpretation is just the probability that a randomly selected item from this population to be between 3 and 4. So technically, this area represents the probability that x is between 3 and 4, and the same as probability that x is greater or equal to 3, less than or equal to 4. Remember, the density curve and the histogram are used for continuous dataset. So for continuous dataset, we don't differentiate between the trig and the non-trig inequality here, because the probability at a single point is always 0. That means probability x equal to 3 or probability that x equal to 4 are equal to 0. So the equal sign here doesn't matter. So the probability density curve basically tells us what proportion of the population falls within any given interval. In this example, the given interval is 3, 4. So that's how we construct the density curve and how we interpret the density curve inferences for the population. Now, for the probability density curve to describe the population, we have some properties. A probability density curve represents the probability distribution of a continuous variable. So remember, density curve is applied for a continuous variable, not for discrete. The area under the entire curve is equal to 1. The area under the curve between two values a and b has two interpretations. It is the proportion of the population whose values are between a and b. It is the probability that a randomly selected individual will have a value between a and b. So that was how we build up the density curve to describe a population. Now let's do one simple practice. Example 1. Following is a probability density curve for a population. A. What proportion of the population is between 4 and 6? B. If a value is chosen at random from this population, what is the probability that it will be between 4 and 6? C. What proportion of the population is not between 4 and 6? D. If a value is chosen at random from this population, what is the probability that is not between 4 and 6? So let's observe this density curve. Remember, the area under the density curve between 2 points A and B has two interpretations. The first interpretation, it is the proportion of the population between the 2 points, and the second interpretation is it is the probability that a randomly chosen item from this population is between 4 and 6. So this area, point 16, is the answer for both part A and part B. So part A, the answer is point 16, and part B, the answer is also point 16. Now we look at part C. What proportion of the population is not between 4 and 6? We see the keyword not here, showing that C is the complement rule, or the complement event with A. A, the proportion of the population is between 4 and 6 is 0.16. So the proportion of the population is not between 4 and 6 is 1 subtract 0.16 using complement rule. So the answer is 0.84. And 0.84 is also the answer for part D. If a value is chosen at random from this population, what is the probability that is not between 4 and 6? So that's how we use density curve to describe a population. So that was about general density curve. In practice, the probability density curve comes with many varieties, many shapes, depending on characteristics of the population they represent. One of the most important density curve we should learn is the normal curve. So at this section, I'm going to introduce the normal distribution. Many important statistical procedures can be carried out using only one type of probability density curve called a normal curve. That's why the normal curve is important in statistics. A population that is represented by a normal curve is said to be normally distributed or to have a normal distribution. So now let's investigate the normal curve to see why it is important in practice. Here is a picture of some normal curve. We have 4 normal curves here. They might be tall, flat, thick, thin, but they have some common properties. The normal curve should be symmetric and center at the peak with a unit peak. So there are certain properties that make the normal curve stand out from a general density curve. The first property is a normal curve should have unit mode. That means exactly one mode. That means one peak, only one peak. The second property is it should be symmetric. And since the density curve, the normal curve has only one mode and it is symmetric, so the mean, the mode, and the median are the same. So those are the first 3 properties that make the normal curve stand out from the general density curve. And if you look on the picture, you see that some normal curve is tall, some normal curve is flat, some normal curve is centered at 0, some normal curve centered at different value. So basically the shape of the normal curve depends on 2 factors, the location and the spread. That's why for normal curve we have 2 parameters. The first parameter is the location parameters and denoted by the mean. The mean mu is where the normal curve center at. And the second parameter is the scale, sigma. Sigma is the parameter tells how widely the curve spread. So here you see that if sigma is large, the curves tend to be flat. If sigma is small, the curve tend to be tall. On the second picture, you see that one curve can be shifted to different center, not necessarily at 0. So the shape of a normal curve again depends on two factors, two parameters: the location parameter, the mean, and the scale parameters, sigma. And one of the properties of the normal curve that is remarkably important is the empirical rule. Here, we consider a normal curve. So normal curve is symmetric, unit mode, and center at mu. The empirical rule is applied for only the normal curve. And the empirical rules say that approximately 68% of the population is within one standard deviation of the mean. In other words, approximately 68% of the population is in the interval mu minus sigma to mu plus sigma. Approximately 95% of the population is within two standard deviations of the mean. In other words, approximately 65% of the population is in the interval mu minus 2 sigma and mu plus 2 sigma. Approximately 99.7% of the population is within three standard deviations of the mean. In other words, approximately 99.7% of the population is in the interval mu minus 3 sigma to mu plus 3 sigma. So empirical rule is one of the most important property about normal distribution. Next, z-scores and standardization. As I said, the shape of the normal curve depends on two parameters, the location and the scale parameter, mu and sigma. So the location tells where the center of the curve is, and sigma tells how widely the curve spreads away from the center. Since the curve have location parameter, we can actually shift the curve of the normal distribution either to the left or to the right. And also, since the curve depends on the scale parameter sigmas, so we also can either enlarge or enlarge the curve vertically. It's basically just like in college algebra, we can use transformation to shift the graph to the left, to the right, and either enlarge or enlarge the picture vertically. So the purposes of standardization is just how to shift the normal curve to the center 0, and how to either enlarge or enlarge the curve until the scale is 1. So a normal curve with two parameters, location 0 and scale sigma equal to 1, is said to be the standard normal distribution, the standard normal curve. So let's look at this standard normal curve. This is a standard normal curve. And for standard normal curve, the center is 0. And the scale, the scale parameter sigma is 1. And suppose a variable z is set to follow standard normal distribution. That means z follow normal with mu 0 and sigma is 1. So this is a special case of the normal curve, the normal distribution. For convenience of computation, usually for any general normal distribution, we will try to convert the general normal distribution to the standard normal distribution. So that process is called standardization. When we standardize a general normal distribution into a standard normal distribution, a value x, any value x on the general normal curve, the original normal curve, would be corresponding to one value z on the standard normal curve. And standardization is basically just making the relation between the value x of the general normal curve and the value z of the standard normal curve. So let x be a value from a normal distribution with mean mu and standard deviation sigma. We can convert x into a z-score by using a method known as standardization. And the z-score z is x minus mu over sigma. So basically the graph will be shift either to the left or to the right depending on whether mu is positive or negative, and divide by sigma to make sure we can either enlarge or enlarge the picture until sigma is 1. So standardization is basically just transformation. So let's do some practice about z-score. Example 2. Heights in a certain population of women follow a normal distribution with mean mu 64 inches and standard deviation sigma is 3 inches. A randomly selected woman has a height of x is 67 inches. Find and interpret the z-score of this value. This question is simple. We basically just follow the z-score formula. So the z-score of 67 inches is x minus mu over sigma. Mu and sigma are both given. So we just substitute them into this equation. And we got 67 subtract 64, the whole thing divided by 3. So the z-score for 67 inches in this population is 1. Similarly, another randomly selected woman has a height of x equal to 63 inches. Find and interpret the z-scores of this value. So the z-score for 63 inches is 63 minus 64, then divide the whole thing by 3, and we got negative 0.33. So when we got the z-score for these two women's heights, we can see that the first woman is taller than the second woman a lot. And here are the two normal curves. The first normal curve is before we use standardization. This is the normal curve representing for the population of woman heights. And the second picture is the standard normal curve. So 63 is an x value from the original distribution. It is corresponding to a z-score of negative 0.33 on the standard normal distribution. And similarly, 67, an x value on the general normal distribution of the normal curve of the population heights. It is corresponding to the z-score 1 on the standard normal curve. So we see that like the shape of these two curves are basically the same, just we use transformation to make connection between them. The last thing I want to talk about today is how to find the area under the normal curve. There are 4 important type questions relating to the area under the normal curve. The first type is finding the area under the standard normal curve to the left of a z-score. The second one is finding the area under the standard normal curve to the right of a z-score. Then finding the area under standard normal curve between two distinct z-scores. And the last one is how to find the area under the general normal curve using standardization. And sometimes on the exam, your instructors, your teacher, your professor might not allow you to use graphing calculator, statistical calculators like TI-83, TI-84. So the safest way to deal with these type of question is know how to find the answer using the z-score table. So in this lesson, I'm going to show you how to use the z-scores table to find a solution for these 4 type questions. Here I include a short version of the z-score table and how to interpret the table. I will walk you through these 4 type questions and show you how to interpret this table. Let's go over the first type, finding the area under the standard normal curve to the left of a z-score. Let's look at this example. Use table A2 to find the area to the left of a z-score of 1.26. So to give you the best illustration, I draw the standard normal curve, and on the x-axis, on the z-axis, I'm going to mark 1.26, the z-score. Remember the standard normal curve center at 0 and the standard deviation is 1. After I have my z-score marked on the picture, I shade the area to the left of the z-score. So the shaded area represents the area to the left of the z-score, and is also the probability that z is less than 1.26. And now I'm going to use table A2 to find the answer. This table is a table that gives you the area to the left of z-scores. So to find the area to the left of the z-score 1.26, I look for the row of 1.2 and the column of 0.06, because 1.26 is 1.2 plus 0.06, and I see that the row of 1.2 intersect with the column of 0.06 at a green square, which is 0.8962. So the area to the left of this z-score 1.26 is 0.8962. So that's how I use the table A2 to find the solution for type 1 question. Now let's look at type 2, finding the area under the standard normal curve to the right of a z-score, and we use the z-score negative 1.44 as an example. So the question asks for the right, the area to the right, but the z-score table gives you the area to the left. So basically we are going to use table A2 with complement rule to find a solution. So the area to the right of negative 1.44 is 1 subtract the area to the left of that value. Now we use A2 table, the z-score table, to find the area to the left of negative 1.44. Negative 1.44 is at the row of negative 1.4 and the column of 0.004. So the area to the left of negative 1.44 is 0.0749, and use complement rule, I have the area to the right is 1 subtract 0.0749, which is 0.9251. So the first type is the easiest because we basically just we just read the table and find the answer directly. Type 2 is a little bit more difficult because we have to apply the complement rule, but type 2 is too simple. Now we go to type 3 question. Find the area under the standard normal curve between the z-scores. Let's take two z-scores as an example, negative 1.44 and 1.26. So we are going to find the area under the standard normal curve between the two z-scores. So how we work on this type of question is just probability that x between negative 1.44 and 1.26 is probability that x less than 1.26 subtract probability that x less than or equal to negative 1.44. And please be mindful that equal sign here doesn't matter because we are working with continuous variables. So if you look at the z-score table, the area to the left of 1.26 is 0.8962, and the area to the left of negative 1.44 is 0.0749. So we substitute these two values into the formulas, and we got 0.8213 is the area between the two z-scores. So type 3 is a little bit harder than type 2. However, working with z-scores is still simple. Now we go to the more challenging type of question, that is finding the area under the general normal curve. So type 1, type 2, type 3, we was working with the standard normal distribution. Now for type 4, we are working with the general normal curve. And to find the area either to the left or to the right or between some x values, we basically have to use standardization to convert the general normal curve to the standard normal curve, because the A2 table, the z-score table, is just applied for only the z distribution, the standard normal distribution. So let's look at this example. A study reported that the length of pregnancy from conception to birth is approximately normally distributed, with mean mu is 272 days and standard deviation sigma is 9 days. What proportion of pregnancies last longer than 280 days? So the question gives you a distribution with mean 272 and sigma is 9, and the question asks for the probability that x is greater than 280. This is not standard normal distribution because mu is not 0 and sigma is not 1. So the first step is standardization. And the way we standardize the problem is just subtract both sides by mu and divide both sides by sigma. So we have the same probability. Now mu is given and sigma is also given, so we got 280 minus mu over sigma is 280 minus 272 over 9. However, do not substitute 272 and 9 into the left-hand side because x minus mu over sigma follows z. So we are going to replace by z. So now we have converted the problem into the z's problem. That means the problem now is converted into the standard normal distribution problem. So go ahead and compute the right hand side. We have, this is probability z greater than 0.98, and 0.98 here is a z-score. So to find the area to the right of the z-score 0.98, we have to use complement rule because the A2, the z-score table, give you the area to the left of a z-score. And let's look up for the z-score on the z-score table. 0.89 is the intersection between the row upon 8 and the column upon 09. So the area to the left of 0.89 is 0.8133, and using complement rule, we have the area to the right of that z-score is 1 subtract 0.8133, which is 0.1867. And on the picture you can see it here. 280 here is the x value with a z-score of 0.89. So basically, the area to the right of an x value is the area to the right of the corresponding z-score. So that's it. That's all for today. Thank you so much for watching my video. I hope you guys find my video helpful. See you next time. Bye.